Welcome to the another session in Frontiers in CFD. Today we have the CFD simulation to analyze the influence of phase change material thickness on the thermal management of lithium-ion cells. So the first objective is to prepare the geometry of lithium-ion cell to define the PCM thickness as a parametric variable, because we'll be using the different thickness of the PCM and what will be the effect of the thickness of the PCM with respect to some parameters like temperature of the cell, temperature at of the total system, and what about the liquid fraction. So all this we will visualize with respect to the thickness. Next is to generate the mesh on computational domain and checking the proper element size for domain and specify the name selection. To run the setup and visualize the result with the parameter study, and to analyze how changes in the thickness impacts the thermal regulation. So these are the today's objective we are having. So this is the specification which we are going to use today. Height of the cell is 65 mm. So that's for the first case, where you can observe 18 mm is the diameter, that is radius 9 plus 3 mm thickness, so 9 plus 3, that is 12. Second case, we are observing diameter 18, that is radius 9 plus 6, that is 15. And the third one is the 9 plus 9, that is 18. So this is how the various combination we are going to check. So the PCM thickness is 3 mm, 6 mm and 12 mm. So we'll see how the variations are taking place with respect to some of the parameters that we are interested in, that is the total temperature of system, cell temperature and liquid fraction. PCM thicknesses of 3 mm, 6 mm and 9 mm. So this is the circle of the cylindrical cell with diameter 18. The thickness here is 3. Second, again the diameter is 18, but the thickness of the PCM has increased. Third one, we have taken the thickness of PCM as 9. So accordingly, if I take 9 as a radius plus 3, that is equal to 12. 9 as a radius plus 6, that is equal to 15. 9 as a radius plus 9, so that will be equal to 18. So accordingly, we are going to proceed for this particular simulation. So let's start with the workbench window. So just search for the workbench option here. So the first phase will be to prepare the geometry of cell. Now we are using the parametric analysis, so that I'm not going to generate each and every geometry for this case, but for the first itself I will generate, and accordingly I will put the parametric option, and accordingly I will go with the second and third one. So this is how the simulation which is done with the parametric values. So let us say go with the fluid flow fluent option. So in fluid flow fluent, just go with the geometry, click on new design modular geometry. So once the design modeler is loaded, first of all set the units. So here set the units to mm. So click on any one of the plane. Here blue, this is green, and this is your red, green and blue. So that will show you x, y and z. So go to the create, go to the primitive. Now in this case what we are going to do is we are having two cylinders. So first of all click on cylinder. Instead of add metal, I will make it add to frozen. So this y component will be equal to 65, and z component will be equal to 0, and now this radius will put the first value with thickness, that is equal to 9 plus 3, that is equal to 12, and accordingly we will generate the first cylinder. So now this is I need to add the cell also. So one more time, go to the primitive, that is cylinder. Now instead of add metal, I will make it slice metal. Y component I will put it 65, the z component I will make it 0, and instead of 12 as a radius, now I will take the radius is equal to 9. So accordingly, so we will generate the second geometry. Now you will see there are two things which has been formed. One is your, if I select this will be your cell, and this is your PCM. So this thickness of the PCM will go on to vary, and because of which I will put the radius one as a parametric option. So right now it is 12, so I will make it okay. So this is one of the thing which I had done with the parametric, so that I will just go on to change the radius of the thickness of the PCM, and accordingly we can do the analysis with the various cases. So this will be in the parametric mode. So this is the first one. This is your PCM. So I will just click on here as a PCM. Second one, we will specify this as a cell. So click this and rename as a cell. So first one is PCM and second one is your cell. So both will be in the definitions. Here it will be solid. Second one will also be equal to solid. So let's go to the workbench window and just click on save button. So go inside, prepare a separate folder. Let us say here. So now we'll define PCM cell with PCM different thicknesses. So first one is 3 mm, then 6 mm, 9 mm. So these are the various thicknesses that we are going to do, and we'll see the heat generation 104017 watt per meter cube. So this is the three things which we are going to follow, and accordingly we'll first save the file. So use the same title which we have here. So cell with PCM different thicknesses 3 mm, 6 mm, 9 mm, heat generation is 104017. So first of all, saving the work. So the geometry preparation is actually done. Now I will go with the mesh option, that is edit. So you can actually close the geometry part because there is no requirement of this particular case now. So let's close this. So now we will generate mesh. So now let's click on mesh. The mesh window will open. So we'll generate the mesh. Now as per the different thicknesses which we are trying, we also try with the different mesh sizes. So here also we'll see select the parametric option. So let's make it fit to window. So this is what is the first one. So I will first generate a default mesh and we'll see how the main number of nodes and elements are. So the number of nodes and elements are 2904. So I'm not interested in that lower values, so I will just go with 0.0005 and I will just make it okay. I will just make it generate. So element size are taken 0.0005 and for that 0.0005 this mesh is generated. So I will select this as again parametric option because I will be generating the results at a different mesh count. So this is one of the count which we are having and accordingly we'll proceed with. So first of all I will go to the geometry and I will go to the PCM and hide all other bodies. So I will rename this as cell boundary. Okay, so what I done is I have specified the cell boundary here. This one. This is your mesh which is generated. So select all bodies. Show all bodies. So this is the PCM along with the we can say cell boundary has been available. Now I'll just click on update option so that uh, it will having the mesh translation to Fluent successful. So these are the two the thing which we had done. Now you can actually close the meshing window. So let's close the meshing window. Now just go back to the workbench window. You will see the parameter set. So what we have tried, we actually tried with the two things. One is the cylinder uh, diameter. So 9 plus 3, that is 3 is the thickness. So total is 9 plus 3, that is the one of the thing which we have tried. Then element size we have took 0.0005. So as I said, like we will be dealing with various thicknesses. So this is one of the parameter which we have considered. Okay, the second parameter which we will be having is 9 plus 6, that is the 15. So that is again your radius. So this is 15. The mesh size will be the same. The third one which we are trying is 9 plus 9, so that is equal to 18, and the same element size we are going to proceed with. And the next process is I will go with the 12, 9 plus 3. Then I will change the mesh count over here. So instead of 0.0005, I just take it now 005. Next is 15. I will again change the mesh count to 0.005, and lastly I will take it 18 and I will change the mesh count to 0.005. One more time I will just go. This is 12. Here I will put 0.001. Then I will go with the 15. Here I will go with 0.001. Similarly, last one, that is 18. Here I will put it 0.001. So right now we have specified the two parameters which are been there. One is your based upon the thickness of the PCM. So the cylinder which is related to the PCM will be having 12 mm, then 15 mm, and we can have the 18 mm as your radius. So accordingly, now we will try this with the different values of we can say the thicknesses as well as with the mesh count. So let's go back to the project one more time. So click on setup, click on edit. Now here I will select double precision, I will put it to 16, and let's click on start button. The setup window has opened. You can click on this here. So next is transient, specify the gravity. So I will put it minus 9.81. Why I selected minus 9.81? Because this is the positive direction, so the gravity will be acting in the downward direction. So go with the model. So I don't want multi-phase model, so I will just turn the energy equation only. Then viscous, I will put it K epsilon. Then enhance fault treatment, thermal effect, and curvature correction. So all these options are available only in the K epsilon model. That's why we have selected the K epsilon model. Next is solidification melting, as the PCM will be subjected to melting, so that's why we have specified the solidification melting also. So no other things will change in the model, so we'll keep it as it is. The next is the material. So here I will specify the material which we are going to use. So first of all, it is your paraffin wax, a liquid. So I will mention this as paraffin wax liquid. So what is the thermal the properties which we are considering? So density I will put it 790. Specific heat rate I will put it 2150. Thermal conductivity I will put it 0.22. Viscosity I will put it 0.001. Sorry, 0.01, not 001. Then pure solvent melting heat 240800. So this is the value. The solidus temperature is 313.6 and the liquidus temperature is 317.7 Kelvin. So let's make it change grade. So this is the first one which we have generated for paraffin wax liquid. Now I will just put it lithium cell. So click it lithium cell. Here also I will put it lithium cell. So the properties which we are considering is for the lithium cell is 2750 as a density. Specific heat I will take it 1250, and thermal conductivity I will take it 1 watt per meter Kelvin. So let's make it okay. And now one more time, just go to the Fluent database solid, and now select the aluminum, make it copy and then close, so here now I will specify the paraffin wax solid. So paraffin wax solid, here also I will write paraffin wax solid. So now put the values of paraffin wax solid. So that is your density is 800, then specific heat is 2000, and the thermal conductivity is zero point 0.2 watt per meter Kelvin. So let's make it create and then close. Now computer at its own will not understand which are the zones, so we need to specify the zones. So the cell should be a solid one, so make it solid. So here, so cell will be lithium ion cell. I need to select the source term, uh, so select one and put it value, that is 104017 as a heat generation per unit volume. Make it apply and then close. So PCM is your fluid, which is zone has been showing. So I will save paraffin wax liquid, make it apply and then close. Now next to the boundary conditions. So here cell boundary contact region. So I will go to the edit and I will select the thermal material as lithium cell. So by default it is available, so you can keep it as it is. Okay, one more thing which I am going to change is I will put some convective heat transfer coefficient, let us say equal to 5 watt per meters Kelvin. So then close this, make it apply and then close. Next is your wall PCM. So go on edit and ensure that the material is uh, paraffin wax solid. So I selected paraffin wax solid. By default it was showing lithium cell. So same way you have to check it for wall cell. What is the material for that? It is lithium cell. Make it apply and then generate. So the boundary conditions things are done. Now it's time to proceed for your report definition. So go to the new area weighted average. So first of all I will say temperature. Here I will say total temperature of the system. Now I will click all the option and select output parameter. So here I will put total temperature system as a report definition 0. So let's make it okay. Now second one I will do surface report area weighted average. So instead of temperature now I will make it solidification melting. So wall PCM and the contact region SRC where the PCM will be present. So I will put it liquid fraction curve report. So let's put it to 1 and let's make it generate. So second report definition we have set, the third one we will set it now. So this is temperature, then total temperature. Now I will select wall cell and I will select the cell boundary contact region. So here I will put cell temperature, so total temperature cell curve. So make it okay. So we have set all the three. Now I'll go with the initialization option and just click on initialize. Once it is initialized, we'll go to the next step, that is calculation activities. So you can select the option of auto save. So I put it 20 because the simulation may run for longer time, and that's why it is important to save after each the time steps. Okay, so new object I will select it contours. So first of all temperature, I will select the total temperature of the system and select all options. Here I will select the float option rather than exponential in order to visualize the scale in better way. So make it save display. So this is how the things will be visible. Select the contour one and here you can put the total temperature system animation 1. Make it okay and then close. One more time, new object contours. So here I will put it solidification melting. Now where is the PCM? Wall PCM and contact region. This is the region I will select. Make it float, make it apply and then close. So make it save display. So this is the PCM region will be visible to us. Now let's click on close. So contour 2 I will make it liquid fraction animation. I will put it, let us say 2, and make it generate. Sorry, next is your contours. I now require temperature. Here it will be your total temperature. So now I will select wall cell and I will select the cell boundary contact region. Instead of exponential, I will make it float and make it apply, and then close. Click on save display and then click on close. So select the contour 3. Here I will set the cell temperature, and here I will put 1 2 3. Let's make it generate. So these are the 3 things which we are done. Now it's time to proceed towards the calculation part. So let us say I put it number of time steps is equal to 10, and now we will can proceed for the next part. So let's one more time just go to the parameter set option. Now in the parameter set option, as you are observing, we have set the report definition, that is total temperature of system, liquid fraction, and we have set the total temperature of cell curve. So all these parameters are actually visible here, and accordingly we can proceed for the next step. So here whatever the parametric study we are thinking of, so according to that we are following, and we will have these 3 parameters, and all these 3 parameters will be calculated based upon your the cylinder, the radius, and second one is your element size. So let's come back to the project, and now let's click on calculate option. So first of all I will just run it for 10, and accordingly then I will increase the time step values. So preferably we were thinking of running it to around 1000 time step, or preferably around 600 time steps, so that we can see the curves. So let's click on calculate, and let's see what uh, the animation window shows us, which contours it is showing along with the curve which we have set in the report definition, which are them are visible, so that we are going to see over here. So this definitely has to be run for longer time in order to visualize it, maybe for 600 second or maybe 1000 seconds, so as to see the solidification and melting, because you will not see the liquid fraction in the initial cases, because the just now the process of heating has started, and the temperature you can see is comparatively lower. So that's why here in the liquid fraction you will see all the scale which is showing 0. There is no such value which has been shown. So when it will show the value, when we will reach to the melting point of the PCM, that time we will see the values which are available here. So as of now it is not there, so this will show you the cell temperature. Then this is the total temperature of cell, that is curve. So another liquid fraction curve, what I said earlier. So this will show you the flat curve, that is at 0. So till the time we are not reaching to the melting point, you will not see any variation in this curve. So next is the total temperature of system curve. So that is again we have generated. Now we have to run this further in order to have the temperature which is going to melting point, and then we can visualize all such results at once, and you can do the parametric study for each and every case. So what is the advantage with the doing the parametric studies? You don't need to put prepare the geometry again, you don't need to put the thicknesses, or you don't need to put the various things which we have done, or you can don't need to change the mesh. So whatever the parametric options we have specified, so they will be by default generated by clicking on the respective icon in the parameter set options. So let's click on the save button first, and then we will proceed for the next remaining steps. So I just click on save button, and now we'll go back to the fluent window. So let's put it some value which is around 190, and then I will just click on calculate. So definitely it will take some long time, so we'll visualize this once we are completed around 190 time steps. So let's click on calculate, and let's proceed. So if I go with the parametric option right now itself, so you can see the temperature is showing it's 300.13, the liquid fraction is showing 0, and this is the cell temperature is showing 300.24. So cell temperature will show slightly higher as compared to the total temperature of system. So this value will change because this is the what we are run for only 10 time steps. So if you run it for maybe next 190 times step, this value will go on to change. So this is how the charts uh, uh, the further can also be prepared, because this file can be transported as an Excel file, and you can copy the data as it is over there. So let's, by that time, just wait for the calculation to complete and to reach to the point which is significantly nearer to the melting point. So we have completed around 339 time steps and flow time. So you can see the temperature has reached to around 308 Kelvin. So you will not see the liquid fraction as of now, because we haven't reached to the melting point. So this shows you the cell temperature. This is again the total temperature of cell, that is curve. This liquid fraction, again it is 0 as of now, because we haven't reached to the melting point. This is your total temperature of the system. Apart from that, if you see the parameter option, you will see variation here. Earlier it was different value, now here it is a different value. So we are running the first case as of now. So accordingly we can run the remaining cases also once this is done. So let's come back to the project and let's wait for this process to get complete. So we'll try to run it for around 1000 or 1200 time steps, so as to visualize the final results. So we are near to around 313 Kelvin. The time steps are 587. So with this time steps, as of now the liquid fraction is not there. Okay, we'll just wait for some time. Okay, so liquid fraction curve, still it is flat. So here you can see the liquid fraction curve, liquid fraction. As of now, we don't observe any liquid fraction here, but shortly we'll see some liquid fraction as we are reaching to 313.43 Kelvin. So the 4 time steps are remaining. So around 600 seconds will be completed. So you will see the calculation complete message. Contours of liquid fraction, as of now it is not there. Here also we can see the flat curve, but shortly we may see the contours of liquid fraction will be visible. Just parameters, we will observe this temperature reaches to 312 Kelvin, and the total temperature of cell it's 313 Kelvin. So let's come back to the project again, and we'll run the simulation again for some 100 to 200 time steps. So first of all, I will run it for 100, and then again I will run it for 200. So this is the liquid fraction. I just click on calculate. So we'll just take a look of what will happen to liquid fraction, because we are slightly near to the solidification melting points. So this is the curve. So we'll wait for some time, and we'll just, after this 100 time steps are completed, we'll see any liquid fraction is visible or not. You can see now the liquid fraction has been visible. So just now it has started. So you can see the contours of total temperature 314 Kelvin. So the liquid fraction has been visible now. So cell temperature, and this is liquid fraction. So you can see the rise over here. So that is the outcome of we can say the higher temperature which has been reached. So you will see the solidification melting process, that melting has occurred. So liquid fraction has been visible here. So once we run this further, we'll see more about this. So the liquid fraction curve is now going up, and you might have seen the temperature curve is slightly getting flat. So this is the total temperature system. So we'll run this further in order to visualize what will happen, maybe around 1200 seconds, or preferably maybe around 1000 seconds. We'll see the results. So you can see the simulation is run for around 800 seconds. So this is the contours of total temperature. This is the contours of liquid action. The contours of cell temperature. And then cell temperature curve likely to become flat. The liquidification curve. Then the total temperature of system, and this is the scale digital. So I'll just click on save the work. And the thing which we are thinking of, like a parametric study, how it can be done. So this is we are shifting now. So you click on parameter set. So first of all, I will save the work here. I will close the fluent window. So we are on it for around 800 seconds. Just remember that. So click on save the button. Now you have to go with the parameter set, and this is the first thing which you are on right now, earlier, before saving. So this is the current state, and you can see 314.42, that is total temperature system. Then here you will see the liquid fraction. Here you will see the liquid fraction, and lastly you will see the temperature of the cell. So we are run it for the first. Now I'll just show you with the current and other thing how I can run the second also. So you can click here, update the selected design point. So once I click on the update selected design point, the second process will start. So earlier we are run the simulation for dp0. Now we are running the things for the second case. So the way we are done previously, everything will be calculated in the same manner, but you don't need to open the fluent window and other thing. So this all process will be done automatically just by clicking on update. But the only thing which is changing right now is, earlier we had the cylinder was 12 mm. Now here it is a 15 mm. So now what I said at the start, 9 plus 6.
So 9 is the radius of the cylinder and 6 mm is your thickness of the PCM. So with that particular thickness of the PCM now we'll get some values of temperatures. So these three again parameter will be obtained. Total temperature report, total liquid fraction, and lastly is your the total temperature of cell. So if I just click on update all design points one by one. So now this is you took for the comparatively finer size of mesh. So that's why uh, it may take some time. So the next points which like 0.005, 0.001, so they may take comparatively more less time than what we did for the earlier one. So in this way, the simulation with variable thickness that can be run, and uh, I'll just show you this. If you go and when this is process is completed, you will see the temperature here also. You will see the liquid fraction as well as you will see the temperature of the cell. So this process has to be done for every we can say the parameter which we have set, and uh, the report definition output we say. So what we have set in the report definition, so that will be visual here, and the Excel chart can also be prepared from this, and you can directly take the data from the Excel file. So we'll wait till the process is getting completed. Once the first one is completed, we'll just do the second, third, and fourth, and so on. After running the iterations for all we can say the design points, so this is how the outcome is. We have the three outlet parameters, that output parameter, that is total temperature of the system, then liquid fraction and total temperature of the cell. So this was where the output the fraction output parameters, and some of the parameter which we are considered for mesh size and the thickness. So here it is your 12 mm as your thickness, then 15, and then 18. So 9 was your diameter, and sorry, 9 was your radius plus 3 mm thickness. So 3 mm is thickness for your PCM. Here it is 6 mm thickness, and here it is a 9 mm thickness. So for all of them we have done it with the different mesh sizes along with we can say the three different output parameter. So you can see, so you can see 314.42, 314.14, 311.15. So these are the temperatures which are been visible. Similarly, if you see the second one, which is related to 0.005 mesh size, 314.82, 314.58, and 311.55. So these are all the design points where you can see the temperature of the system. Liquid fraction is also visible over here, so with various values which are been there, and the last one which goes shows you the temperature of the cell. So in this way, so various things uh, where the things are simulated for different values of mesh size along with the different thicknesses of the PCM, and these are all the temperatures which are available for the results. So these are some of the sample images with the PCM thickness of 3 mm. You can see the liquid fraction, and then again you can see the thickness 3 mm, the cell temperature. Next is the PCM of thickness 9 mm. So you can see the temperatures, a liquid fraction which has been available. So this is again the cell temperature. So these are the observations during the CFD simulation. We are done with the different element sizes, and we are done with the different thickness of the PCM. Accordingly, we have calculated the total temperature of system with the help of the CFD simulation, as well as the liquid fraction which is available, and the last one is the cell temperature. So from this graph, we can observe as the thickness of the PCM increases, the total temperature of the system decreases for all the element size. Smaller element size shows slightly lower temperatures compared to the larger element size. Next is your liquid fraction. So the liquid fraction decreases significantly with increasing PCM thickness, and this trend is consistent across all element sizes. At smaller element sizes like 0.001 mm, the liquid fraction is higher, indicating the better phase change behavior due to the finer resolution.
Next is your cell temperature. So the cell temperature decreases with increasing PCM thickness. Higher element size like 0.005 tend to show higher cell temperatures compared to the smaller element sizes for thinner PCM as compared to the thinner PCM. What we can conclude is increasing the thickness of the PCM reduces the total system temperature, the liquid fraction and cell temperature improving the cooling efficiency but slowing the phase change process. Smaller element size provide better resolution leading to the more accurate prediction of phase change and the temperature distribution.